Welcome to this introductory video on atoms in the periodic table. This video series is intended to give you an overview to several things. First off, we'll talk about the question of why atoms. Why do we need atoms to describe matter? We'll move on to what's in an atom and how it's structured, how we can identify and organize elements, and then what is the mass of an atom. So as far as a brief and very incomplete history of atoms, the first time the word atom actually shows up is within Greek philosophy from a philosopher named Democritus, and he proposed that an atom was a necessary philosophical construct, and we'll get to what that means in a little bit. Between about 1000 to 1650 AD, essentially the idea of atoms was forgotten. People ignored it, but this period between 1000 and 1650 is the period of the alchemists, where they're trying to take matter, chemical matter, invaluable matter, dirt or iron or lead or whatever, and turn it into gold. And so this is sort of the birth of modern lab chemistry, trying to turn one thing into another thing. Again, we didn't have the concept of atoms, though, within science. That starts showing up in the 1770s to 1810s, the atomic revolution. So a series of important experiments, people like Lavoisier, people like Priestley, are learning about the structure of matter on a molecular level, or I should say the observations that they're making suggest that there must be this atomic or molecular level to the structure of matter. In the 1830s to 1870s, we took this a step further. We started understanding the relationships between the known elements and the way that they were organized, and discovering that there's this periodicity to the way that you can organize them. And this, again, reinforces the concept of atoms, and it adds a whole lot of credence to it. And the best place where we really cement the idea of atoms into our own understanding of chemistry is the 1890s to 1930s, with the advent of what we call quantum mechanics. We'll go into this a lot in detail later this semester, but in quantum mechanics, we really start to be able to probe the structure of an atom itself, the way atoms are set up, the way molecules are set up, and that becomes very important for us to finally really understand and figure out what makes elements and molecules tick. So we start with atomic theory, and again, this is not a new idea. This was something that was first proposed by Greek philosophers like Leucippus and like Democritus. The word atom comes from the Greek word atomos, which means indivisible, and it was a philosophical thing. If you were trying to come up with a philosophical way to describe the universe and to understand the world around you, eventually Democritus said you needed something that couldn't be broken down any further, and that was the atom, that was the atomos. And again, this wasn't something that got a lot of traction in science. There was no reason to believe it. There were no observations as such that made it really obvious to people until much, much later. In fact, you notice it's 1808. John Dalton, who was an English school teacher, formalizes atomic theory. He wasn't the first person to propose it, but he formalizes the principles of it. And there are three important principles of atomic theory according to John Dalton. They all have varying degrees of correctness, as we're going to see as we go through this semester. The first one is the idea that elements are composed of tiny, indestructible particles, and those particles are what John Dalton and other scientists call atoms. I highlight indestructible in red because indestructible isn't quite true. We're going to find out in a little bit, and you probably know from your own science classes, that atoms can be broken down into smaller subatomic particles. Dalton's third atomic principle, so we'll come back to the second, but the third atomic principle is that all atoms of a given element have the same mass and other properties, and those properties are distinguishable from other atoms. So hydrogen is different from helium, and Dalton said it's because their masses are different. Now, I've highlighted that in red because that turns out to be not quite true. Again, we didn't know about subatomic particles at the time, and that has to force us to modify the theory a little bit. Now, the last important principle of atomic theory that I'm going to point out to you is that atoms combine in simple whole number ratios to form compounds. And this is really what Dalton was seeing in his own time. People like Lavoisier were doing experiments where they found that everything reacted in fixed ratios, or everything was produced in a reaction in these fixed ratios. And so what they said was that the things that make up matter are combined in these simple whole number ratios, and we call those compounds. Let's move on to what's in an atom and how it's structured. And again, this is something that you're familiar with from your own science background. I would be pretty willing to bet. It's also something that we're going to go much more into detail in another couple of units. At the early 20th century, we knew that an atom was composed of three main types of particles. The first type of particle is called protons. Those are positively charged. We symbolize those with a lowercase p. Sometimes you'll see p plus because a proton is positively charged. Protons, it turns out, identify an element. Hydrogen is hydrogen because it has one proton. Zinc is zinc because it has 30 protons. Protons are found in the nucleus, and the nucleus is just this big, massive center of the atom. What about neutrons? Well, neutrons are also found in the nucleus of an atom, and neutrons have no charge. Those can vary among the elements, so there's a version of hydrogen that has one neutron. There's also a version of helium that has one neutron, and so that's not a reliable way to identify a particular element, but they can vary among the same elements. So there's a version of hydrogen with no neutrons, there's a version of hydrogen with one neutron, there's a version of hydrogen with two neutrons. All of those are different from each other and have slightly different behavior, but they're all hydrogen. The third subatomic particle is an electron, and we symbolize that with E- because electrons are negatively charged. And electrons identify whether an atom's in an elemental state or a charged state. So elemental, neutral hydrogen, has one proton, positive charge, one electron, negative charge, and those balance each other out. On the other hand, H+, the positively charged ion of hydrogen, has one proton, +1, and 0 electrons. And so you're left with a +1 charge. And where are electrons found? Well, for now, all you need to know is that they're found somewhere outside the nucleus. Electrons are away from the nucleus. The nucleus has the protons and neutrons, and we'll talk much more about that later. The other important thing about electrons that we're going to find out later, it turns out that they are part of the basis, or they are the entire basis for how atoms react with each other and form compounds. So I just want to point out to you that protons and neutrons are much larger and much more massive than electrons. Protons 10 to the negative 27 kilograms, but an electron is about 10,000 times less massive than the electron. By the way, because these are cumbersome numbers, 10 to the negative 27, 10 to the negative 31, and hard to conceive of, what we do is we talk about the masses of protons and neutrons and atoms in what we call AMU, or atomic mass unit. And an AMU is 1/12 the mass of a proton atom that has 6 protons and 6 neutrons. So instead of saying 1.7 times 10 to the negative 27 kilograms, we say that a proton has a mass of about 1 AMU, and a neutron has a mass of about 1 AMU. And so that just helps us keep track of and understand and conceptualize very, very small things using this different type of unit.